So we came across a class of problems that are hard to solve, but easy to verify. And that led us to the beginning of the thread of understanding the context of ZK and what it came from, namely the decomposition of computation into two parts, an expensive search and an easy verification by examining a piece of data that we called a witness. So now we have some idea of the nature of computation. But there are, of course, many types of computations. Some easy to solve and verify, like adding numbers, for example. That is a problem that is easy to solve, but easy to verify as well. And some that are hard to solve and to verify. They're hard in both ways, like, for example, determining the best next move in a chess game, and so on. So we need to step back and understand the universality of computation. So we don't want to just speak of those specific problems. We want to speak in generality. And as we will see, the notion of computation is universal, as I said previously. And the concept of reduction will continue to be the rock on which we stand. It is, as I said, the one concept that ties everything together. So today we'll begin to unpack this notion of universality. And our goal is to start speaking of classes of problems. So we want to understand the computational cost, the verification cost, and the possibility or lack thereof to solve a problem to begin with. Some problems, as we will see, are not solvable to begin with. Today we will set the stage for two important reductions. We'll see if we have the time to get to them. But we'll begin by setting the stage for these two important ones. Okay, so just fix that. From the question that you see now, you can already know that we're going to go all the way back. We're going to go back to the foundational bricks of human knowledge, basically. This is because, why are we doing this? It's because questions about computations are actually equivalent to questions about mathematical truth in general. And they're equivalent to questions about the foundation of mathematics itself, as we will see. We will circle back to the concept of like witness, where we stopped yesterday, but we will by then hopefully be equipped with the necessary tools to put that thing in a coherent universal context. And that's our primary goal here. Remember, the primary goal of this whole series is to understand the context in which ZK fits generally, understanding our place in the epistemological forest. Okay, so we are talking about mathematical truths. We are not, we are concerned with mathematical truths, those that we can prove using austere logic with as few axioms as possible. For the more general, say, subjective type of truths, that would be something that can be discussed in the philosophy department, or it can be discussed at your place of worship if you are into that. So what is mathematical truth? Look at the following sentence. It's a meaningless sentence with a bunch of symbols. XP-E X dash. It's composed of these three letters, P, E, and hyphen. An X is not actually a letter, it is a placeholder for one or more hyphens. So X can be substituted with one or more hyphens. Okay. And let's assume that this sentence is true, self-evidently so, no questions asked. Let's just take it as absolute truth. This bunch of symbol, this statement exactly is true. And now we're going to follow a rule mechanically and blindly, which says if X PYEZ is true, then adding one more hyphen here and there is also true by derivation. It's true by derivation from the previous truth. Okay, so we have a self-evident truth, and we have truth that we can derive from previously established truth by adding one dash in the middle and one dash at the end. Okay, we will take this rule for granted as well. Just like X, Y, and Z, they are also placeholders. Think of them as placeholder for hyphens, for one or more hyphens. So these are examples of self-evident truth. They are true because we take this as truth. Okay, this is an example in which X is a placeholder for one dash. This is an example where X is a placeholder for two dashes. See X here, two dashes, and this X, two dashes, but we added one at the end. And these are examples of truths that are derived, okay, from previously established truth, because according to our rule, we can always add one in the middle, one more dash in the middle, and one more dash at the end, and the result will also be true, will also true by derivation. So obviously there are infinitely many truths, right? Some of them are self-evident according to this. Some of them are true by derivation. We take one and we add hyphens, one in the middle, one at the end, and that's a derived truth. There is infinitely many of them, obviously. Now, at the beginning, I said, let's take this meaningless statement as true, okay? But is it in fact meaningless? If we ourselves, we chose to interpret P as plus and E as equal, then these statements begin to have meaning to us. They begin to convey the notion of arithmetic addition. This true sentence, self-evident sentence, says 1 plus 1 is equal to 2. We are interpreting P as plus and E as equal. And the dashes, we are interpreting them as numbers, natural numbers. So it's not that meaningless. It can have meaning if we bestow upon it such a meaning. So if we want to be more precise about it, we will say, okay, that this infinite set contains all sentences in this hypothetical PE hyphen language that encode for all valid arithmetic additions over the set of positive integers. Okay. We could encode the three symbols of our language with numbers. So we could assign these binary numbers to the P, E, and hyphen. Okay. And we can treat strings as numbers. So this statement, for example, once we encode it following this simple encoding scheme, it becomes this number, binary number. Or if we prefer to look at it in decimal, it will be equivalently this number. Okay, so now we are looking at statements as numbers, which means that every dot in this infinite set, okay, once decoded back into the P, E, and hyphens, it corresponds to either a self-evident or a derived truth. Okay, this infinite set, okay, of self-evident and derived truths, they are all natural numbers, but not all natural numbers will correspond to a correct encoding. Therefore, our infinite set is a subset of the other infinite set of natural numbers. Okay. Now let's create a machine or a human, or we'll call it a bouncer, that will decide at the door of the set which number is belongs to this set and which does not. We will give this machine or this human clear instructions, which are extremely really easy. It's those derivation, it's the axioms and the derivations. And there is no intelligence required for us to decide if the number belongs inside this or outside it. And the instructions could be as simple as the following. We take a number as input. We convert it into binary. We generate every truth, self-evident truth in blue, or derived truth that has the same length as k. And we put it in some container. Okay, so this is a finite number of statements that are of the same length as our input. Once we created this container S, which could be very large, but it's finite, we loop over each element in that container. And if S is equal to our input, we accept. We say yes. The number encodes for a valid statement, a true statement, and it belongs to the set. Otherwise, we say no, we reject. This number is not a valid truth. It's not true. So we call this set of numbers, we call it the language. It is a language. It's a bunch of numbers which, when decoded into the PE and hyphens, it corresponds to something precise. And we call this set of instructions, we call it the machine. We call it the machine. Now, think about this. The machine instructions themselves, these instructions, although they could be written in some alphabet like English, they could be written as a Python program, they could be in assembly, it doesn't matter. We can also encode it as numbers as well, right? We just take the alphabet and we assign a binary number to it and we encode it and it becomes itself a number. The machine is itself a number. And that number, obviously, it doesn't encode for a truth, but it encodes for a machine. It belongs here, basically. Okay. So now we have the language and the machine, and they're both encoded as numbers. We establish a connection. This is the machine. This red dot right here is the number which encodes for our machine in whatever language we have written it and in whichever encoding we have chosen to encode it with, basically. So this is our language and this is our machine. We could imagine more languages and more machines as well. So this is the English language. Yeah, the set of the infinite numbers, each of which is encoding one of the infinitely many syntactically correct English sentences. And this is the machine that decides whether a given input, a statement in English, is correct or not. Does it belong to the language or does it not? And this parser could be written in Java or some language. It could be, your favorite librarian who's deciding is it correct or not. This is a language, the DNA sequences of encoding for valid panda genomes. And this is a number encoding the biospecs of the female panda womb, or the software, more realistically, the software program that is simulating it. This is the set of prime numbers, or the encoding of those prime numbers in our favorite encoding. And this is the primality testing algorithm, or the software implementation of that algorithm. More languages and machine. This is the GCD. This is a list of triplets, ABC, which encode for the statement that C is the GCD of A and B, and so on. So We have languages and we have machines. And languages are precisely what we call, in mathematical terms, truth, and machines, they are precisely what we call proofs or algorithms. The proof means something is in a set, something is out of a set. So they are the same object. In fact, the concept of machine or algorithm in abstract terms is a generalization of the classical notion of proof, the classical mathematical notion of proof. You may be familiar with proof as, the classical Pythagorean theorem, things like that, those proofs. The notion of algorithm is, in fact, a generalization of that. It is simply a step-by-step procedure for deciding if a number is in a set or outside of a set. So we kind of trim down these otherwise vague concept into this very, very austere and clear thing. Is a number in a set or outside of a set? That's basically what it means. Okay. We will, of course, later on, we will define the abstract notion of a machine, etc., in a reasonable details. So to be absolutely sure that you're aware of these equivalences and aware of the fact that they are all natural numbers as far as studying them is concerned, we will define that, we will define that later on. Of course, it is of no practical use to think of the algorithm of your, let's say, DeFi yield-bearing token in its numbered representation. In practice, it's not useful for us to think of our algorithms in terms of in the same way we are doing here today. But it is very useful if we are trying to make assertions about the notion of algorithms in general and their relations among themselves and their relations with their subjects. What is their subjects? Their subject is the truth. Algorithms, they operate in truth, and they decide, is this sentence in or out? Is it true or not, as we'll see. Okay, so we saw an example of an axiomatic system. This is an axiom and a set of derivation rules. And we bestowed upon it a meaning which corresponds to arithmetic addition over the set of positive integers. But we don't want to do that every time. We don't want to go through this exercise every time, right? Every time we want to talk about a certain truth of interest in every domain. By the way, when I say the word axiomatic system, I mean axioms plus truths. This is what an axiomatic system is. It's an axiom, something that is self-evident, and the corresponding rules for derivation. This is what an axiomatic system means. So we don't want, let's call it apt-specific axiomatic systems. What we want is a universal axiomatic system. Similar to how we don't have a machine to do word processing and a different machine to watch videos and a different machine for spreadsheet, etc. Instead, we have these general purpose universal machines on top of which we run any app-specific algorithm, right? So we want to do the same thing when talking about truths. We do want to talk about each truth in every domain in its own axiomatic system. We want a universal axiomatic system through which we can speak of any truth in any domain. So we'll go back to the 19th century. There was a lot of excitement about set theory. It was in fashion, and some people, they were trying to use it to construct that universal system by which we can establish something is in, something is out, something is true, something is false. So let's get a glimpse of it. Consider the following infinite set. It is the set of even numbers, and of course, it is infinite. Why? Well, if you claim that it is finite, then there must be a number n that is the greatest largest number, but n plus 2 is also even and it's larger than n. Therefore, n could not have been existent. So it's infinite. That's obvious. But I followed these logical rules to establish that it's infinite, just to get you used to the notion of logical establishment of truth. Okay, we can define this set symbolically. Obviously, we can define it as this. It's a set. For every n in n, it's 2n. Using this notation, when we use notations like this, we avoid confusion. We try to be precise. And this is the set of natural numbers itself. It's also infinite, of course. We can pair up every element in A with every element in B. Okay, 0 to 0, 1 to 2, and so on. We can create a mapping between the two. But we can also pair from B to A. Namely, we can write f of B is equal B over 2. That's a function from B to A. And the same thing, function from A to B. From A to B, the function is 2A, and from B to A, the function is B over 2. So what does it mean? This pairing between the two means that the two sets are in fact of the same size. This is despite the fact that, as you can see, the set B is skipping over the odd numbers, right? B does not contain 3 and 5 and so on. But despite that fact, okay, we managed to pair them up with A. So they must be of the same size. This can be counterintuitive, but the bijection between the two sets tell us that infinities can have the same size, despite the fact that one is a subset of the other. And the size of an infinite set, we call it the cardinality. So these two sets have the same cardinality. Similarly, we can define the set C. Okay. It is this infinite set of the powers of 3. So it's 3 to the power 0, 3 to the power 1, 2, 3, and so on. The set of powers of 3. And we can also pair up every element in A with every element of C. The pairing, basically, the function from A to B is basically log of base 3. And sorry, the other way around. So f of A is equal to 3 to the power A, and f of B, of C, sorry, is equal log of base 3 of C. So we created a bijection between the two, which means they must be of the same size as well. So these threes are all infinite, and they're all of the same cardinality or the same size. Okay. But now consider the following set of real numbers between 0 and 1. Okay. We can order that set in some lexicographic order. Okay. All the way down. You can choose a way to, you start with the numbers that have 1 digit and then 2 digits and so on. That have 1 digit in the first, that have one number in the same digit, but the rest is 0, and then in the second digit and so on, in some order, basically. The numbers that you see here, they're just random. They're just for illustration purposes. Can we do the same pairing between this set and n? So let's assume that such a pairing exists. We can define a function from R to n and from n to R, such that there is a bijection between the two. That's our assertion. that a pairing does exist. Let's assume that. We will now construct a number between 0 and 1, a number that should indeed belong to this set, as follows. You see, I highlighted here in red the first digit of the first number, the second digit of the second number, the third digit of the third number, and so on. Okay. We will construct the number as follows. Okay. We will take that first digit and we're going to change it. We're going to just add 1 to it. We're going to flip it. So instead of 0, it's going to be 1. And then the second digit, we're going to take the second digit of the second number. We're going to change it to 7. The third digit of the third number, and we're going to change it to 4. The fourth digit of the fourth number, and we're going to change it to 3, and so on. So now we constructed this number, which should belong to the set R, okay, because it's between 0 and 1. But by construction, it differs from every number in our supposedly ordered list by at least 1 digit. It differs with the first one in the first digit. It differs with the second one in the second digit, and so on. Which means the bijection that we assumed exists between the two sets must have been false. That assertion was, that premise was false, because we found a number that could not have existed in the pairing. So this is the number that we, that we constructed. What does this mean? It means that R is larger than N. The set of real numbers, just those between 0 and 1, is larger, has a higher cardinality than the set of natural numbers. So results like these, they were fun and exciting in the mid-19th century, and there was a lot of excitement about set. Everyone was hoping that set theory has the potential to lay the foundation for the axiomatic system overall. Why? Because with sets, we are able to make finite statements that make assertions about infinite objects. So it seems to be like a power tool, basically. So the idea was this: let's define mathematics itself using sets, the primitive mathematical objects. And then we're going to start rigorously defining fundamental concepts like functions. Well, a function is basically a set, right? Function is a set with pairs that pairs an input to an output, and so on. So we can define the concept of a function using sets. And we add some notation that says, an input cannot be paired up, cannot be paired to another element. So if we have here A and G, this will not be a function. We call that instead, we call it a relation. Okay, so we are able to specify this notion of a function using sets and so on. So let's get started, and that's what they were saying. Let's get started and start defining everything else in mathematics using the concept of sets. So for example, instead of saying that 3 is anything that has the threeness property, which is a vague statement, it's a vague statement, and we're trying to establish is something rigorous and complete, we'll say 3 is the set of all sets that contains precisely 3 numbers. So, and we can take this statement and we can express it symbolically. It's the set of all sets and so on. The alphabet of set theory are things like, brackets, obviously the arithmetic addition, the exponents, the equal sign, there exists, there exists and the negation, etc. These are our alphabet. Remember the alphabet that we saw in our primitive addition language, the dash, P, E, hyphen, etc. In set theory, these are the symbols that we are dealing with. And it's finite. We have a finite set of symbols. There exist the brackets, for all, the plus sign, the minus sign. What about numbers? Well, we can define just the number 0, and then for 1, we can just say 1 is equal to the successor of 0, and 2 is the successor of 0, and so on. So we can have a finite set of alphabet with which we can basically describe anything. This is actually Fermat's last theorem. For example, we expressed it using that alphabet. And it says no 3 positive integers x, y, and z satisfy this equations for any integer value of w of greater than 2. Notice how positive integers and any integers, these are 2 different statements. Positive integers, any integer, right? So we had to use that. We had to specify that when we expressed the theorem in our English language. But in axiomatic notation, we did not have to specify both concepts, okay? Because it is captured by adding 1 here. All we had to do is add 1 here and put 3 in the exponent. So by precisely, this is basic. What I'm trying to say is this is way more precise than expressing this in English language. We can capture it much more precisely and without any confusion. Unfortunately, cracks started appearing in this naive set theory, despite the initial excitement. It turned out that, set theory cannot just be let loose to define arbitrary sets. We get too excited too quickly, because that led to logical potholes, like this one, S. S is the set of all sets that are not members of themselves. If you look at it, if you stare at it for a while, you will see that S cannot be defined. We can define S symbolically as S is the set of all sets that are not members of themselves. So, it's a syntactically correct statement, and yet it cannot be defined. Why can this set not be defined? Well, what about S itself? Is it a member of itself? Is it a member of itself? Well, if it is, we violated the definition, which says not a member of themselves. But if it's not, we violated this part, which says all sets. It means we are missing one set. So S itself can neither be in nor out of itself. So this is a paradox. Create a paradox, or we can call it a logical pothole. Okay, and our expectations and our hope is that we stumbled upon a universal axiomatic system with which we can express everything. But now we saw something that we want to define, that we defined, and it's correct according to the syntax and everything, and yet it's neither true or false. It's something weird in between. Notice that it's not that this statement is false. It's neither false nor true. It's just something weird in between. It cannot be established. So the excitement was crushed, and now we are back to square one. Math nerds went back to the drawing boards and they kept searching for a non-leaky formal axiomatic system that doesn't allow for these problematic paradoxes to even arise. This is Hilbert, their, their ringleader, basically. They wanted something universal and airtight. Airtight means all truths can be expressed or derived using this axiomatic system. And B, no falsehoods can erroneously appear as truths. So we want it to be completely airtight. We will not be, we do not want to be able to use the axioms and the derivations to arrive at a statement that is actually false. The system should prevent that. But at the same time, we want it to be able to express anything we want. This just was one of the motivations. These logical pesky potholes were one of the motivations. But there were also other motivations like ambiguities in concepts like functions. We take it for granted today, but at that time, you will take two mathematicians and they will have slightly different notion of function. There was also some holes in previous axiomatic systems and so on. So the pressure was on for something airtight and universal. And to summarize the goals of what mathematicians were trying to accomplish, they wanted a system that is complete, consistent, or sound. This is soundness. And decidable, meaning truthfulness or lack thereof of a statement can be determined by mechanical application of the rules to the axioms. No intelligence, no vagueness, no if this, if like, it's very mechanical. And if you think back about that primitive PE hyphen language that we talked about, it is complete because all valid arithmetic additions are contained in it. They are expressed in it, obviously. It is consistent and sound. A false number cannot be an encoding of arithmetic addition. We will be able to detect it basically using the derivation rule, where we insert a hyphen in the middle and a hyphen at the end, will never ever lead to an invalid addition. 1 + 1 is equal to 3, something like that. And it is decidable as we described in that simple algorithm that we. So we wanted the same thing for the entire system of truths, entire mathematical truth. Complete, all truths can be proven, consistent, no falsehood can be proven, and decidable. There is a mechanical way of deciding something is in or out. This is not actually Bernard Russell. This is Sam Elliott, the actor. But I imagine if there was ever a movie about that period, Sam Elliott would probably play Russell. Russell and Whitehead, they said we will use austere logic to hunt this system down, the system we're looking for. That's the complete, consistent, and decidable. We'll go back to basics. Because, you know, if you want to define a system, you got to start somewhere, right? You have to start somewhere. What do you do? So Russell said we'll start with logic, austere logic. And at that time, around that period, logic actually matured. So logic itself became symbolic and it became much more precise. Logic is actually ancient, of course, and this is how we, as humans, this is how we used to conduct logical arguments. We use something called syllogisms, right? This is called a syllogism. But now that logic is more symbolic, it means that we can build logical primitive that is so austere and so basic, and we can use it as Legos to construct this axiomatic system that doesn't have any potholes. Logic, the nice thing about logic is it doesn't assume much. Yeah. The only thing you assume in logic is things like, well, the thing is equal to itself. That's something we can all agree on. And it's something that shouldn't lead to any problems. It also something like if x is equal to y, and z is equal to y, then it must be that x is equal to z. Two things that are equal to the same thing are equal to themselves. That is also something we can accept. So logic is nice and austere. And the hunt was on. The hunt for a complete, consistent, and decidable system was on. These are the properties that we want from the universal system of truth, a foundation of mathematics itself. And then once that is settled, we can start establishing truth in other domains, in physics or whatever. Notice that completeness, I have two different colors here. Completeness and consistency, they are properties of the language. Remember, the language and the machine, the truths and the proofs. They are properties of the language itself. The language, every truth can be expressible in the language. No falsehood can be expressed in the language. But decidability is a property of the algorithm, or equivalently, as we said, of the machine. The fact that a statement, the truth or falsehood of a statement, can be decided using a finite number of steps and a clear and unambiguous number of steps. So Russell and Whitehead, they authored this gigantic set of volumes. It's a foundational text to accomplish exactly this, starting from the most primitive, minimal and primitive set of logical Legos. They built up a whole axiomatic system. They were so careful. They were so careful in laying down those logical foundation to make sure that no leaks show up, just like that paradox that we saw. They were so careful that it took 400 pages of foundation just to establish that 1 + 1 is equal to 2. So if you read these volumes, you are not going to be convinced that 1 + 1 is equal to 2 until page 400. That's how careful they are. Now, this is an example of working hard. But two other chats where they were working smart. So now it's time for us to, to introduce Gödel reduction, and followed by the Turing reduction. And together, they will help us understand whether or not and how we accomplish these three properties. Okay, so Russell and Whitehead, they were not yet finished. They were continuing to, publish more volumes of this, more foundational axioms. But these two guys, they were working on something else. They took a different approach. They were basically working smart. So I'll stop here if you guys have any more questions. Okay, we will we'll now get to the Gödel and Turing reductions. We'll start with the first one. I'm not sure we'll be able to finish both of them, but we'll see. So, okay, so let's step back and think about the problem. When I say we want a complete, consistent, decidable system, it seems like the problem seems intractable. But we will rely on our good old friend of reductions to see how we can actually crack this issue of finding of establishing these three properties. We're going to use it, we're going to establish that using reductions. So suppose that someone came up with such a system, okay? Whether or not you can think of it as this proposed system that they came up with or something else. Let's just call it L. whatever axiomatic system. And it's claimed to be complete, consistent, and decidable. Okay. It's complete. That means we can express any truth about it. Truth in number theory, truth about cities and people, DNA sequences, PE system that we saw. Okay. Can think in the abstract sense, you can think of objects and relations. This system is powerful enough to express, to describe any relations between any objects. This is basically what it means. So suppose this system exists. And as I said, take this to the most abstract imagination you can have. We will begin by the following. This is like our reduction starts with the following. We will assign a number, an ID number, to each symbol in the alphabet. Okay. So remember, this is the alphabet with which we can express anything. This S, for example, is the successor that we will use to define natural numbers, for example. So S of 0 is the number 1. So our alphabet is finite. We can just use this. We can use just two symbols, 0 and S, to define any number. And we assigned an ID to each of our to each symbol in the alphabet. This is the alphabet of the supposed system that is airtight. Next, we are going to convert every statement into a unique number by raising the next prime number to the ID and multiplying through. So for example, this is a statement expressed using that alphabet. We are going to convert it into a number by raising the first prime, which is 2, to the ID of the first symbol, which is 2, because the ID of S is 2. Okay. So you see here, for example, this one, it is the ID, 9 is the ID of the plus sign in our alphabet. And it's in the 5th position in the statement, 1, 2, 3, 4, 5. It is in the 5th position. So we are going to take the 5th prime number, which is 11. The 5th prime number is 11, and we're going to raise it to the ID. So we do the same thing for all symbols, and we multiply through. That gives us a unique number, and it's unique to this statement. Why is it unique? This is due to the fundamental theorem of arithmetic. This number will be unique because of prime number factorization. It's a gigantic number, obviously, but it's all we care about is that it's finite and it is unique. For each statement, there will be a unique number. Okay, so each statement is now a unique number, and in step 3, we're going to take a proof. And what is a proof? It's just a series of statements. We're going to take a proof and also assign it a unique number by raising the next prime to the unique number of that statement. So suppose that the first statement, got the number n1, second statement n2, and so on. These are the unique numbers as we did in step 2 previously. We generated these numbers. We will now take the first prime and raise it to the first number in the proof, the second prime, 3, and raise it to the second number corresponding to the second statement, and so on. Okay, we'll take the kth prime and raise it to the number corresponding to the kth statement in the proof. And that will also give us a number again, and that number will again be unique. It will be unique to this exact proof. Okay. It's good to pause and think about what we have done. We came up with a generalized reduction, which takes any axiomatic system L. Okay. Don't forget, we started here. We assume that someone came up with L, an airtight axiomatic system that is able to express all truths, does not express any falsehoods, and is decidable. This is where we are. And we said, whatever that alphabet is, okay, here I showed an example here, but whatever that alphabet is, we're going to give it IDs. We use those IDs with the prime factorization property to convert each one into a number. We did the same thing with proofs. And now we have a unique number for statements and a unique number of proofs. So this is a generalized reduction, which takes any axiomatic system, any claimed axiomatic system L, which could be the hottest next axiomatic system in the mathematical circles. And it's claimed to be airtight, no paradoxes, no limitations, etc. And we turned that alphabet into IDs, ID numbers, and then turned the statements into unique numbers by the property of prime factorization. And we turned the proofs, which is a collection of statements, into numbers as well. This is where we are. So to summarize, we started with an alphabet and we encoded it. We gave an ID to each symbol. Notice that I am describing a generalized reduction here that you can follow to apply to any axiomatic system that someone is claiming. And then we reduced each statement into a number, a unique number. This is important, a unique number. And we turned a series of statements into numbers as well. We raised the first prime to the first statement in the proof, the second prime to the second statement, and so on. And now we are going to go meta. Okay, we're going to talk about statements about statements, statements about proofs. Okay. Let's have a little setup first. In logic, f of x is a propositional function if it evaluates to true or false when supplied with some concrete value x. A function, if you are not familiar with a function, is basically an input-out device, right? With the properties that an input cannot result in two different inputs. It's always unique. The output is unique per input. Okay, so for simplicity, if you want something concrete, you can think about a Python function that returns true or false based on the integer you pass to it. Is it even or is it odd? Or something like that. So the point is, a propositional function is kind of hanging in the air. It's neither true or false until we supply it with a concrete x. This is something I'm sure you're familiar with, but I just want to emphasize it. Propositional functions, they are nothing but statements themselves, right? But they are statements that get a concrete number representation the moment we supply a concrete value as input. So for example, here, W. They assume a truth or falsehood once we supply a concrete number. But as a statement, they are kind of like hanging in the air. So this, in our reduction, in our arithmetization, okay, this is basically the nth propositional number, the nth propositional function represented by a unique number n. And W is also a number that encodes for some statement S. Now consider this statement. The ith proof, we are using pi to represent proofs, the numbers that encode for proofs. The ith proof proves the jth propositional function when supplied with a concrete value W. This is what this statement says. Now, what about this word, proves? I am writing it in English for simplicity and to avoid some like tedious details. But we can indeed capture it with our arithmetization schemes. We are turning our axiomatic system into numbers, but here I am being a bit sloppy and using the word proves instead of showing you the symbolic representation of it and the numbers that correspond to it. I'm using it for simplicity. So this is me being sloppy for the sake of simplicity. But to give you an intuition how this, how this statement is actually can be turned into a number, we said that a proof is a series of statements. We raise the first prime to the number representing the first statement, the second prime to the number representing the second statement, etc. The last statement in a given proof, okay, should be, the last statement in a given proof should be this. It should be this. So we raise whatever prime we have reached so far in constructing this statement or up to this point. We raise it to the number representing this one according to our step, according to this step. Okay. Which means that some prime raised to the number representing this is a factor in the ith proof. It's a prime factor in the ith proof. So this is, if you didn't get what I just said, don't worry. I am just trying to explain to you how this word proves, which is I'm using it to avoid some tedious details, can in fact be encoded in the same way that we encoded the statements and the proofs. Okay. In other words, think about the word proofs as an abstraction to make things simpler for us. We are interested, okay, after this short intro about propositional functions and about statements, this is a statement about a statement in the system. The ith proof proves the validity and the truthfulness of the jth propositional function. We are interested in a specific type of propositional function, namely propositional functions that take as input their own number. So the jth propositional function, does it evaluate to true or false when the input to it is j itself? Okay. If you're thinking like, this is contrived, what are you talking about? It is, but bear with me because this is the setup that we'll use it to lay down the hammer, basically, as we will see shortly. This is the negation of that statement. It says there does not exist an I such that the ith proof proves the jth function which when supplied by itself. This is the negation of that statement. We are continuing with the setup. We are building into something here. We're building into a statement that we'll see now. This statement overall overall should evaluate to true or false. Our system, the system that is claimed to be airtight, should tell us if this one is true or false. I mean, it means that it itself, the outside statement, it itself is a propositional function. It's a propositional function about a proof of a propositional function. If it's itself a propositional function, it means overall, it can be a number itself. It will be a unique number itself. Okay. So let's call that unique number of this overall statement, let's call it the kth propositional function when supplied with J. So J gets in here and it gets substituted or inserted in the inside. So let me repeat that in English. The kth propositional function when supplied with J is a number encoding for this whole thing. We established a connection between two numbers in our system, J and K. And that's why we're saying meta. We are talking about statements about statements. We're making a statement about two numbers. We are ready to state an important statement. So if you are daydreaming, please wake up. It's an important. We are reaching the end of our reduction, and it's a statement that has huge implications. Okay. What happens when we supply K itself to f of K? This K here gets substituted in the inside, and it instantiates this part. This becomes concrete. And this becoming concrete makes the whole thing becoming concrete. Remember, a function is hanging in the air until we supply it with something concrete, which we did here. We supplied a K, and it became concrete. And what the whole left side says, what does the whole left side say? It says there does not exist an I, such that the ith proof proves the kth propositional function when supplied with K. It should not be true. It does not exist. I hope you are seeing what we're doing now. We are in a self-referential, weird self-referential loop. The inside makes a statement about the outside. This will be the second time we encountered the self-referential weirdness. Remember the very first paradox that we ran into? Remember that first paradox which says S is the set of all sets that are not members of themselves? There was a self-referential weirdness going on, which led to a paradox. And here, you can think of this one as sort of like it's the same animal, okay? But in a much more sophisticated, much more generalized, much more destructive way, because it completely destroyed the notion of a universal, complete, and consistent axiomatic system. We came up with a statement that makes assertion about itself. It says there is no such proof about f of K. If propositional function K is true, then it must not have a proof in the system, as the left side is asserting. The left side is telling us that. The left side is asserting that the k propositional function should not have a proof in the system. Because if there were a proof for it, then the left-hand side is false. And fk must be false. Okay, but wait, if there were a proof for it, then it must be true. But for it to be true, there cannot be a proof for it because then it must be false. So if it's true, it must be false. If it's false, it must be true. And we are in a strange loop, basically, because of this self-referential thing. Now, looking from the outside, we can see that fk is true, it should be true. It cannot have a proof in the system, but we can't express that in the system. We cannot express that within the system. The system is incapable of expressing the truth of that statement because of this contrived construction. So this concludes our construction and our reduction. We reduced from any general axiomatic system into statements about arithmetic numbers, unique numbers. And what we have arrived at, this statement right there, it puts a nail in the coffin of the dream for complete universal axiomatic system. Basically, any system conceived or yet to be is necessarily incomplete. Whatever system you come up with, I will construct this statement following the reduction that we came up with, the arithmetization into numbers. I will come up with this statement, and your system will not be able to assert its truthfulness, despite the fact that from the outside, we can see that it should be proven. So this is our first reduction, and it's by the Austrian logician Kurt Gödel. And as I said, he's one of the guys who likes working smart as opposed to working hard and trying to come up with an actual implementation of that system. He just proved that it cannot exist to begin with. Because there exists at least one statement, this statement, that cannot be proven within the system. If you are confused, let me simplify it for you. Okay. What this statement that we constructed, and we tried to be as concrete as possible, except for this part, which we abstracted away for simplicity. What it's saying is that if k is not provable in the system, okay, but the overall, we ourselves, looking from the outside, okay, we can see that overall it should be provable in the system because it's a correct statement. If you're still confused, you can think of it as a concrete, arithmetized way of expressing this exact statement. Socrates says, all Greeks are liars. Okay. Us from the outside, we can take a leap and go beyond the syntactic meaning of the statements. Okay, we can go beyond the syntax and say, yeah, all Greeks are liars. Despite the fact that, like Socrates, if you are very adamant about just following the syntax, you will say, well, is Socrates telling the truth or not? But from the outside, we can make the leap ourselves and say, yes, all Greeks are liars, for example, or not. All Greeks are not liars. We can settle this weird thing into true or false. So what we have basically, the message, the take-home message is the liar paradox can be systematically generated, constructed from any supposed universal axiomatic system, which means there exists at least one statement that cannot be true. Here's one more metaphor to help you understand what we have done. Okay, you can think of the axiomatic system as a record player. Okay, and it is claimed to be a universal record player, meaning if you put any record on it, it will play the sound perfectly. That's the claim. What we have proven is that there does exist at least one record, which, if played, the echo that it creates from the surrounding is so perfect for the record player to self-destruct, to basically explode. You know how sound waves sometimes, like specific sound waves, they break glasses in churches and things like that. You can think of it this way. There is a record which, when played, its echo back will result in the destruction of the universal record player. So what does that mean? It means that the claim that this is a universal complete record player is false. It's not complete. There is at least one record that it cannot be played. Now, one might say, okay, the statement that we constructed is kind of contrived, and it's kind of a useless statement anyway. It's nothing that we use, what kind of functions do we deal with in our daily life? We deal with the transition functions of the Ethereum blocks, a transition function from one block to another, and it's precise and it's nice, and we don't care about this contrived nonsense. But, the answer is, well, it still counts because it tells us that it's useless. It's fruitless to it is fruitless to work hard on these axiomatic systems. Okay, we have to, it gives us a reality check. So it still counts. That's one. But more importantly, there is actually an example of a natural or a useful statement that also cannot be proven within any axiomatic system. And if you are interested, you can look into this. Okay. But for our purposes, this is what we have accomplished so far. We established that a complete and consistent, we established that the completeness is impossible. There does exist a statement which cannot be proven within an axiomatic system. It's basically the liar paradox expressed in fancy arithmetized form. But the consistency also, the impossibility of a system proving its own consistency, it also follows from the results of what that we had. It follows from this result as well, but we are going to skip it today. The consistency, basically what Gödel did subsequently to establishing the impossibility of completeness, he started from the assumption that the system is consistent, and then he derived a contradiction by proving that such a system must contain a proof for this statement for it to be consistent. So he established an equivalence between a system being consistent and a system containing a proof for this. But we already know that the proof cannot contain a proof for this statement. Therefore, the premise is false. The premise that the system is consistent is false. But we are going to skip the details of how he proved that, because it follows from this, basically. It's easy, but we're going to skip it. So today we are over time, so I will stop here for today. And tomorrow we are going to, sorry, not tomorrow. We're going to give you the weekend actually to look at Circom material. We're going to share a Circom starter kit today, so you guys can look into that. But on Monday, we are going to tackle the last property, decidability, and we're going to establish the possibility or lack thereof by the Turing construction. Where is this leading us? To zoom out completely so we can understand where we are. We are talking about computation, the nature of computation. And we said computation and truth, they are exactly precisely the same thing. And we said that algorithms and proofs in the mathematical sense, they're absolutely the same thing. They are a generalization of, algorithms are generalization of the classical notion of algorithms. And at the end of the series, you will see that more concretely and more precisely. We did this, we established this by the Gödel reduction. the arithmetization with prime numbers, etc. And we're going to do this also with a reduction as well. And finally, if we have time on Monday, which we may not, because today we did not get to finish decidability, on Monday or Tuesday, we will have, probably Tuesday, we will have the last reduction, probably the mother of all reduction, the Cook reduction, which will finally put everything in perspective and ties every, it clears out any dust that we have generated so far. So I'll stop here. I'll take any questions if you guys have. Let me look at the chats. Yes, Chen asked, yeah, exactly, we cannot have a complete and consistent universal system. We are, there are truths that are beyond provability. And we cannot ever generate a system cannot ever generate a proof about itself saying, hey, I am consistent. No falsehood could ever be generated. We cannot have that guarantee. It seems beyond our reach, at least in this formal way of looking at mathematics, which is the only way. And I should say, since this result was published, it had a huge implications, obviously, and it had a huge implication even in philosophy. It's basically put philosophy out of a job, basically. So, you know, philosophy now is like scouting for something to do. So yeah. Any questions that you guys have generally? It doesn't have to be about today's material. If you, I will publish the slides so you can go over it again. And what we have done today and what we will do on Monday will set the stage for the last reduction. Gödel and Turing will set the stage for the Cook reduction, which is the one that is most relevant to the ZK stuff. And it's, I call it the mother of all reductions. Okay, if there are no more questions, thank you guys. I know we are over time, so I appreciate you. And I will talk to you in the chat.